Have you ever had that great pleasure and sometimes that great agony of putting an addition onto your house? And you know what a fabulous feeling it is to, once you're done or sufficiently done, to have all that new space. It's just a glorious, mind-expanding feeling, isn't it? So a couple of years ago, when I was living on the Big Island before moving here with Nemesis to the island of Kauai, my next door neighbor made a substantive addition to her home. She was living in one of these beautiful little old Japanese farmhouses. It was just darling. We so loved it. And she finally had the opportunity to build out her garage, which was attached to the house, and create an art studio. So she was so excited about this. It was a year-long endeavor, and it was refinishing the floor to make it less of a garage floor and more something that was studio-like, and putting up all sorts of screens around the side to keep the bugs out, putting in this beautiful, fabulous, wide garage door opener. And you know, it changed things. For example, with that garage door opener in place, normally it was kept down, sometimes, and so it changed the entryway, because when it was down, it was kind of a hassle to like lift it up just to go into the house. So the entryway was different. The process, the flow was different. The way that space was used was different. So here we are. We're about to introduce, we're at this penultimate moment, not the ultimate, the penultimate, of having a new neural network architecture, a class of architectures really. And it's going to change things. So here's the important point. If, as Geoffrey Hinton says, we should start all over. Now, okay, first of all, we're not going to scrap what we've got. We're not going to do any algorithm shaming, okay? What we've got are some very, very good algorithms, but they're very limited in their functionality and their purpose, even though they've been giving the appearance lately of being, ooh, wow. Still, what they're based on, their fundamental core equations, is limited enough so that we know we're not going to get much in the way of real general intelligence out of them. Specifically, the key architectural elements that we've got are multilayer perceptron-based things that obtain their connection weights with some form of stochastic gradient descent, backpropagation being most known and loved. Then we've got the whole class of energy-based neural networks that started off with the little hop field, then it was the Boltzmann machine, followed very quickly by the restricted Boltzmann machine. Then when Hinton invented contrast or divergence, there was a 16-year gap. It was about only 4 years before he and Salakutinov published that first big paper, and then the game was on, deep learning. Deep learning was the new thing. And then we've had, from the whole notion of restricted Boltzmann machines, we've also had GANs, generalized adversarial networks. So we've had these two methods, one where backprop is used to finesse the weights in a deep architecture, and the other where backpropagation and energy-based neural networks, the restricted Boltzmann machine, are used competitively, egging each other on, so to speak, to improve each other's results. Both of them fabulous. We have convolutional neural networks to do vision. Most recently, we've had transformers, which have transformed natural language processing. And now we have a lot of natural language-based text generation of all sorts of things. But when we settle it all down, the notion of a generative AI is really simplistic. We have, on the one hand, a statistical mechanics baseline, the Ising equation, where the unique tweak that defines it as a neural network system is that the connection weights between the nodes are individually adapted, whereas in the classic Ising equation, there is a one-size-fits-all connection. It's not really a connection, but interaction between the nodes. Brilliant breakthrough to have achieved that. If you've read some of the Hinton papers, and you've noticed that what seems to be a very abrupt segue, when he stops talking about here's the energy equation, and that's the one that we typically refer to as having activation energies for the nodes, and then interaction energies between the nodes. And then all of a sudden he seems to be talking about something very different. Gibbs sampling, Markov chains, how it is that we are gathering our data. That's the entropy. Now the important thing, I know a little bit of a digression, but it's going to come together. The entropy in the neural network is parameter free. Parameters are limited to the activation energies of the individual nodes and the interaction energies between them. You set up the entropy term with your data collection. And also, it has to do somewhat, of course, with the distribution of activations in the input data set. Gets a little subtle. We're not going there. At least not today. But that's the Ising equation. It characterizes, it's the fundamental basis for all energy-based neural networks, and transformers are actually derived from that in the sense that the nodes in the transformer system are vector-based nodes. That is, their spins, their on-offness is a vector quantity as compared to the simple Ising system, the energy-based neural networks, the RBMs and all such, where it's on or off, either or a simple scalar. So, okay, energy-based neural networks using the Ising equation, transformers more advanced, but still the same notion, so to speak. In addition to the neural networks methods, we have latent dirichlet allocation, or LDA, which is well known and well loved, and it's a segue, at least intellectually, to variational inference. Reinforcement learning, variational inference, and active inference, almost as a subset of variational inference, are our primary decision-making, planning, and inference method. We addressed all of this in some depth in our previous YouTube. You can see the thumbnail for it right here. There are only a handful of things that are worth talking about. First of all is it a neural network? We've just gone through that. The second is, are latent variables involved? Because one of the things that we found is every time there's been a significant breakthrough, there was a latent variable that was getting introduced into the mix, and generally a good deal more than one. We looked at the training methods. Gradient descent is clearly one. Then the other one is minimizing the free energy. That's what you're really doing in the energy-based neural networks, which are the Boltzmann machine family. Now, a few of the things that we mentioned in that last vid were the Kullback-Leibler divergence and Bayesian probabilities. Kullback-Leibler is used typically to introduce the statistical mechanics. Kullback-Leibler is a divergence, and while it can be generally expressed, what we're typically after is a divergence between the model and your actual data. And you're trying to bring the model and the closer to the data by careful selection of model parameters. And that's what you are varying in the variational inference. If we do a little origami folding of this Kullback-Leibler divergence, it takes us straight into a statistical mechanics free energy equation. Now, that free energy equation gets expressed two different ways throughout the whole panoply of neural networks machine learning methods. If it's a neural network, we go back to the Ising equation and individual connection weights between the nodes. If it's not a neural network, if it is variational inference, then we're dealing with a free energy equation where we do not specifically identify individual connection weights, yet it is still statistical mechanics, and we're still minimizing the free energy to arrive at equilibrium to obtain the results that satisfy the equation. The other key feature that we identified across all these systems was the use of Bayesian probabilities. And that is, every time we have a latent variable, typically you're going to have a Bayesian probability involved, explicitly or implicitly. That's our handful of methods. There's not that much in there, and when you really look at it, it's not that complex. So now that we're considering what could we possibly have that we haven't had before, so we're going to start by looking at the obvious suspects, latent variables. Okay, let's keep that. In the last vid, we discussed this important little nuance, and that is that early in the introduction of neural networks, we quickly decided that we wanted to have the minimal number of latent variables, because if we had too many, let's just take a normal multilayer perceptron neural network as an example. If we have too many nodes in the hidden layer, then we have those classic problems of nodes becoming too specialized. They learn to recognize one pattern, but they don't generalize. Or nodes that are lazy, they never learn anything, or nodes that duplicate each other. So we quickly figured out that the game was to not have too many nodes. And of course you can't have too few, or you can't solve your classification problem or whatever problem you're dealing with. And the same holds true in a Boltzmann machine. That became a truism. It became one of those things that we never really questioned. So what we're going to suggest here is that let's consider an alternative. Let's consider a road not traveled, where all of a sudden we have a lot of latent variables. Now, I'm not going to do architectural specifics with you. In fact, as a quick layout of what we're going to do over the next few videos, we're going to, in the next vid, describe the architecture. In the video after that, go into the necessary equation in a bit of depth, and then we'll start looking at code, honest to God, for reals code walkthroughs. And we'll start to follow that up with code documentations, V&V, everything that we need to do to get a little bit solid with the code. And just as a spoiler alert, we need to introduce a little bit more into the basic code that we've got. And further spoiler alert, we don't have the full architecture in code at this point, and there's absolutely no nice little Keras system that you can just, swipe down some scripts and, plug and run. On the other hand, there is some Python code that we can start with, and it'll be kind of fun, because the important thing for us right now is the really important thing. It's new toy. And we are all just desperate for a new toy because you've been running the same algorithms for a while. So what we're going to do today is scope out what we're expecting when we have this new architecture. First, a lot of latent neurons. Now what we're going to do with this is apply statistical mechanics in a very different way. We're going to go back to some fundamental basic stat mech, Ising equation like stat mech, but we're going to do something very interesting with the entropy term that'll give us a huge range of possibilities that have not really been explored or exploited up to now. The second thing we're going to do is allow for the possibility of neurons staying active and having varying degrees of decay. We'll also allow for different kinds of interactions amongst the neurons that would stabilize some of them so that we don't have to have that sausage-making machine impact that we've had up until now. Right now, the real problem in neural networks of all sorts has been the temporal one. It's that sausage machine thing. You put something in, turn a crank, get out a sausage. Put another thing in, turn the crank, get another sausage. If you're not putting something in, you're not getting something out. We've got our workarounds. We have LSTMs, long short-term memory networks. They're a little bit artificial. They don't really feel natural to us, do they? We've had a lot of luck lately with transformers. Do we really have something that handles temporal processing the way that we want? Not yet. That's been one of the big limitations, something that we want to address with this new architecture class. So what we want are capabilities like this. First of all, holding a thought. You stop putting something in, and the thought process doesn't automatically disappear, and it doesn't automatically just stay stagnant. We can allow for a little bit of perturbation via noise, a little bit of softening the edges around whatever classification or other process it's doing without having to totally degrade the system. Okay, we're calling that first process holding the thought. Put something in, and it's semi-stable, graceful decay over time. The second notion is what I call that reminds me. That is, you put in something, it holds that thought for a little bit, and if you start to allow it to gradually decay, but allow a little bit of perturbation, a little bit of soft stimulus, maybe even a partial notion, you get this association that can build up with repeated experiences over time, allowing the neural network to have a capacity for soft, gentle associative memory, that reminds me kinds of experience. And the third, the final temporal attribute that we're thinking of is California dreaming. I'm calling that in reminiscence of an old song. So the idea is if you put something in and you're not even giving it more stimulus, you're just allowing it to have a little bit of perturbation, a little bit of noise in the system, allowing it to mentally wander, so to speak, looking at clouds. What can it come up with? Now, there's a huge difference between this class of neural networks and what we've got right now. I'm calling this a yang versus yin kind of relationship. The neural networks that we have now are very focused. They are very linear in their methods, so to speak. They are very goal-oriented. We measure their performance in detail, and we're very excited when we can get a new level of performance. If we can take object recognition, for example, from a certain percentage to just a few percentage more, wow, that's so exciting. And we do it by adding typically in more of the same. And that's why we're not getting general intelligence out of them, because they are very explicitly directed in their capabilities and achievements. So with something new, if we're going to start off and have something very different, we don't want to be as clamped down. It's a little too early in the game to ratchet up all the little bolts and screws on this system. Instead, we want to allow some room for exploration. This gives us some ideas about what we'll envision with this next class of neural network architectures, which will unfold in substantial detail over these next 3 videos, addressing in order architecture, equation, then finally starting in with a bit of code. And as we do the code, we're going to start also building out the necessary physics, which is not yet completely and explicitly developed. You know that we want a fun new project for the summer. This can satisfy that need. We're adding a few thoughts here, just something for you to muse upon while we prepare the next vid. Let's introduce the notion of the kind of architecture that we're moving towards. By playing a little mental game, we're going to do a contrast and compare on 2 kinds of physical architectures, not computer, not neural network, just simple physical. In the time right after World War II, there was devastation in Germany, in Russia. There was a desperate need for buildings to house people, to house new government functions, to take care of all the needs of the population. And what happened then, especially in East Europe and in Russia, was something called a brutalist form of architecture. Simple, severe, immediately to the point, no frills, no wasted anything. Stark. Typically a little bit unimaginative, because the idea was simply to get things together as fast as possible and make them functional. Got it. That same kind of architecture, a little bit more refined, has had appearances in the United States, in England, in other places throughout the world. It's still characterized by a strict and severe assemblage of basic, simple forms. Now, contrast and compare that with some forms of Indian architecture that were used for palaces and temples, and that kind of architecture had all kinds of detail in it. It had architectural elements that would connect parts of the building to each other, often in a long succession, a lot of lateral connectivity. It had nuance and detail that turned out to be surprisingly functional. Now, the reason to bring this up is that we've been, over the past approximately 50 years since we've introduced neural networks, working with a variation on the theme of brutalist architectures. They're simple and to the point. A convolutional neural network, for example, is an assemblage of layers, and typically, for example, using very simple elements like ReLU. These architectures have served a purpose, and they've served it very well. Here's another theme that we can consider as we evolve this next class of neural networks, and that is the idea of parallel processes. You have parallel processes in the brain. There was some recent work showing that new functions were exhibited in the basal ganglia that evidenced parallel processes. Link in the description box below. That's going to take you to the blog post. Blog post takes you to a number of articles. Look for parallel processes in the resources and references section at the end. Now, Just because we add an addition onto the house does not mean that we don't use the previous portion of the house. That may continue to be the most dominant portion used. Similarly, if we're adding in a new class of neural networks architecture, it doesn't mean that we're going to replace or eliminate the earlier ones. They can operate side by side, especially if we're looking at the new capability to be some form of softer processing. It doesn't need to be activated in the same way that our primary neural networks have been. It can be an ancillary process. It can be a parallel process. So we're going to allow for these possibilities. In this new form, we might allow for more lateral connectivity. We might also allow for more subtlety, more nuance, more versatility in the kinds of connections that are allowed. So that's going to be one of the things to consider as we open up to new possibilities. So thank you for joining me. It's so much fun to be with you. I look forward to seeing you in the next video. Have a lovely day. Please go to themsys.com, hit the About menu option, do the opt-in. With these YouTubes, please do the like, subscribe, and hit that notify bell, and we'll let you know not only when there are new YouTubes, but also blogs and other useful materials. Thanks for joining us. Have a lovely day. This is Aliana Moren from Themsys.